All right, I think we'll give it one more minute here before we get started. All right, I think we'll get going. So welcome everybody. Um, just a reminder, we're going to be recording this webinar and feel free to ask questions throughout using our Q&A feature. We're going to have Frank Chang from my team joining us on the Q&A, and I'm Abby Lindberg. I lead GelSight's applications engineering team. So once again, thanks for joining this webinar on pits and particles, quantifying corrosion, surface cleanliness, and more using GelSight. And with us, we also have Thierry Mantel. So I'll pass it over to Thierry to introduce himself and kick off the webinar.
Yeah, thank you very much, Abby. Hello, everyone, and welcome to this new webinar. I'm Thierry Mantel, the VP of the Global Distribution and Key Accounts at GelSight. We have seen during the last webinar that scratches and dents can easily be measured with the GelSight portable system on any kind of material and also directly on the shop floor. During this webinar, we will see how pits and particles can also easily be identified and measured using the specific functions which have been developed and implemented in our GS mobile software. Abby will illustrate the use of this function on practical use cases, like the detection of early stages of corrosion, as well as the measurement of particles and even the rating of the cleanliness of components. Corrosion, you know, is a phenomenon occurring in our daily life. It can be defined as the degradation of material due to chemical reactions with its surrounding and its environment. When we think about corrosion, we immediately have in mind metallic materials like steel, aluminum, magnesium, but we also need to know that corrosion occurs also for materials like polymers or even concrete. And the consequences of corrosion are not only cosmetic, but unfortunately can lead to really catastrophic failures. And we all have in mind, the collapse of the Genoa Bridge in 2018 in Italy. The origin of this tragedy comes from the failure of steel cables supporting the bridge, which were presenting corrosion. So it's once again, and we have all other critical cases like that. I will not enter into too many details. Corrosion is a complex phenomenon and which present different typology. It's very important to know that during this webinar, we will essentially focus on the early stages of corrosion, and which are under the form of pits or buildup. We will not be able, with the imitation of the GelSight technology, to identify corrosion, creating galleries under the surface. These will not be addressed by GelSight. The second part of this webinar, we address particle counting and sizing, which are also very critical for different applications, from additive manufacturing processes to when I was mentioning, to rate the cleanliness of components in the space industry, for example. Cleanliness is critical in space industry. The presence of particle can significantly affect, the lifespan, even the malfunction of a spacecraft system. I have in mind, I think it was in the years 2000, the loss of a satellite simply because there was a leak of propellant, the thruster propellant, which was due to a particle. So cleanliness of components in this industry is really key. In both cases, we will see that GelSight technology brings a unique way to rapidly bring precious information directly on your components without the need to bring them in a laboratory or to subcontract the work to a third party. So this is once again what we will show you today, and I will let Abby show you all these functions on very typical examples.
All right, thanks, Thierry. So before we get into some of the examples, let's just start with a little bit of an overview about how GelSight works. So I've got our Series 2 system here. I'll hold it up. And basically, we have a camera and a lens and an illumination system. And when I click this button, I'm actually taking 6 images, one with each one of these banks of LEDs illuminated. And we take the 6 images with the 6 different lighting orientations to get 3D data. Now, in conjunction with that, we have our gel sensor. And we can see the gel sensor has a red pigment layer on it. And that's what lets us look at surfaces regardless of their optical properties. So glass, metal, textiles will all look the same to us. So I'll go ahead and share the GelSight software screen here. And we'll go live. And I'll just press my fingertip into the sensor here so that you can get an idea of the resolution. I'm gonna press it over here too. I've got 2 cameras going. All right. So with that, let's get into some examples of actually using our pit detection and particle detection functions. So the first example that we have is actually this small piece of glass here that I'll hold up. And it has a bunch of pitting on it. So let's take a scan of this and let's measure the pitting. So I'll just press the probe onto the surface of that glass and click the button to take the scan. Probe down. And the 3D data has generated, so we'll open up our scan. The first thing we always like to do is look at our scan in 3D. So I'll click our 3D button here. And here's that surface. I'll scale this up a little bit so we can see some of the pitting even better just in the 3D model here. So I'll jump back over to the analysis view and let's select pit detection from our list here. We can run pit detection on the whole field of view or a region of interest. I'll just draw a box for this example and we'll click Analyze. And we can see the algorithm detecting all of the pits or all of the negative features in our region of interest. We get a table output with every single pit that was found. In this case, looks like 153 pits. And we can see all of the characteristics of each of those. We can sort the results based on, maybe let's sort it by depth in this scenario. And I'll click on this first one and it'll actually take me to the pit that was highlighted in that table. So I clicked this first one. This is the deepest pit. And I can see this blue dot that represents the deepest point of all of the pits that were found. So we can see that max pit depth on the right-hand side here being reported as 35.75 micron. We see some other outputs here that'll be good for some other applications that we'll talk about, some other use cases. But let's walk through what options we can see here. We can see our number of pits. We can also see our coverage percentage, which is relevant for applications like porosity. We'll talk about that as well. We can see pit minimum and maximum, and those are actually referring to the minimum and maximum diameters of the pits that were found. And then the pit depth, which we already talked about. So from here, we can also filter any of our results. So if we wanted to ignore pits until they were a certain depth, we could customize whatever we're viewing that way. We could say we only want to see them when they're greater than, a certain value. If we want to export this table, we can right-click on it and export it to a CSV file or copy it to a clipboard. And then we also have our standard PDF report generation, where we'll be able to see and customize the output, and you'll see the outputs that are from the right-hand side, like that maximum pit depth or minimum and maximum diameters. So let's jump back into Analyze here. And let's talk about some of the advanced parameters for pit detection. If I click the pencil icon here, we'll be able to see the list of parameters. And we have some options for nominal feature size, clipping plane depth, and min and max depths and diameters. So we're going to get into some more detail about nominal feature size and clipping plane depth. These two parameters are used by our algorithm to help find the pits. And then the rest of the parameters that we have here are used for filtering them. So the first two will affect the algorithm. The rest of them will filter similarly to how we can filter on the table down here. Using the filters on the right-hand side here allows us to keep those filter settings for running routines and really automating the workflow with pit detection or particle detection to come. And we also have an option here to include ROI border particles, which we'll talk about with another example later. But this basically includes or excludes pits or particles that are found along the border of your region of interest. So with that, I think I'm actually going to share a slide here to help illustrate what the nominal feature size and clipping plane depth are doing. So let me just share that here. All right, we've got this one. So the nominal feature size is what you're going to enter. It's going to be the approximate size of the pits or particles that you're looking for. And we use that nominal feature size to apply a Gaussian filter to the surface to find a reference surface that will then be removing to really highlight the pits and remove the form of what we're looking for. So we're basically applying that filter based on the approximate size of the features to then be left with just the pits rather than the pits and the form of the surface. And then we also have our clipping plane, which basically takes that filtered image, filtered surface, and decides where we're going to start, setting a threshold for where we're going to start considering something to be a pit versus just below our reference surface, something we want to ignore. So we can see on the right-hand side here on the bottom, an example of using 5 micron as a clipping plane depth on this surface. So we can see we're including some of these smaller pits outside of the larger one that we're looking at. And on the right-hand side, you can see when it's set to 20 micron, we're only going to be considering that deeper pit as our result. Another example of this would be maybe you have kind of a W shape at the bottom of a pit. Setting that clipping plane depth will determine if we're going to consider that to be one pit, measured from the reference surface, or if we want to consider that to be 2 pits with the peak in the center of the W crossing over that clipping plane. Now, I'll highlight again that these parameters are just used for finding the pits. So we actually do something different to measure them. This is just to locate where the pits are in our region of interest. And the next step will be measuring them. So to measure all of our pits, we're actually using a local plane around the pit that we found. The local plane has a planar fit to it to accommodate for any sort of difference in perpendicularity. So we're basically just taking a box around the pit that we found and assigning a local plane to that to measure the deepest point with respect to that plane. So with that, I think we'll switch over and we'll go over some of our other use cases that we have for pit and particle detection. So we'll switch back over to our software over here. And we'll jump back into capture mode. So one of the main applications that we have for pit and particle detection, well, I guess for pit detection specifically, is going to be part marking. So I've got one example here that we'll take a scan live of. I've brought this knife, brought the butter knife in since we're in the office. But we've got a stamped text here, and we'll take a scan of that. So for part marking applications, there's typically a spec on the depth of that part marking. It has to be deeper than a certain depth so that the part marking is legible, but it also can't be deeper than a certain depth because at that point it might have a structural effect on the part that has been marked. So let's go ahead and we'll take this scan here, something like that. And we click the button to take the scan, and the 3D data is generating, and we'll open that up now. So let's use our pit detection algorithm for this. And we'll just draw a box around the text like that. And click Analyze. All right, so we can see it picking up the text pretty nicely with the default settings. But I'm going to make one change based on what we just learned about the nominal feature size, because we're seeing some areas that aren't really counting as part of our pits in these letters here. So one quick check that you can use to help you pick your nominal feature size is one of our manual ruler tools. So I can just come in here and maybe we'll measure the width of this manually. It's close to 400. So I'm actually going to go into my pencil icon here, and we're going to set this to be 400. And I'll click the Analyze button. And we can see that overlay really nicely highlighting the text that we're looking for. The biggest indicator that your pit detection algorithm is detecting your pits correctly is going to be that colored overlay. So if you're happy with the overlay, then you're going to be happy with the measurements that you're receiving too. So let's pull up another example of part marking. So this is stamped text, or we could apply to machine text as well. And let's look at maybe some dot keyed text here. So we've got some dot marking, which is pretty common for a lot of part serialization. And let's add our pit detection algorithm on this. We will do something like this here. And we'll click Analyze. So we can see it really nicely picking up all of the dots on that text there. And we could also take this and set up pass-fail criteria for this text as well. So we could say, if we've got the max pit depth being reported here, we could set a min and a max tolerance on those pit depths. All right, so I'm going to jump back to capture, and let's take another scan to cover another use case. I mentioned the coverage percentage and how we could use that for porosity. So for this example, let's look at this resin 3D printed sample. We've got some porosity going on here where the resin didn't fill completely. So let's take a scan of that. So I'm just going to press the probe onto the surface of that. We can see the gel conforming into all of those holes there. And let's go take a look at that. All right, so we're going to add our pit detection function again, just like we've done for all of the other examples. And I'll draw a box in the area, something like this, and we'll click Analyze. Now this one, you can see the surface texture, we're picking up a lot of pits in the surface texture as well. And maybe we want to ignore that because we only care about the pitting from the porosity, not the actual texture of the surface. So let's go in and let's take a look at our advanced settings again. So the pits that are interesting to me are a little bit larger. So I'm just going to set this to 200. And maybe I only care about pits once they've reached 50 micron deep. So I could set this to 50 here and click Analyze. And now we're left with just the pits that we were looking for. Now here's where the ROI border particles comes into play. You can see there's a couple on the edges of this field of view that aren't being detected, and I can choose to include or exclude those. In this case, if I wanted a coverage percentage over an area, maybe I do want to include them. So I'll check this box and we'll click Analyze. And we can now see those ones along the edge being picked up as well. So for an example, an application like porosity, maybe we do want those, but in another scenario where we are specifically interested in the diameter or the distribution of size of something, maybe we don't want to include particles that aren't full, where their full size isn't in the measurement results. So now Thierry talked a lot about corrosion, and obviously corrosion is in the title of the webinar. So let's start talking about corrosion as well. So I'm going to open up a couple of scans that we've taken for that. Let's look at this scan that's corrosion around a casing hole. So I'm going to add our pit detection function here, and I'm going to use our polygon tool to kind of build a shape around this hole. So we'll do something like this here. Something like that, and we'll click Analyze. And we can see, actually, from a different lighting orientation, we can see some of that even better. So I'm pretty happy with the way this looks with just the default settings. But Thierry, maybe you could talk a little bit about this scan and corrosion around casing holes and what you've seen in the field.
Yeah, this is a typical case you see in a shop floor of or maintenance hangar. This come from the casing of a helicopter engine operating close to the ocean, and just with a single scan, the technician, the operator, is able to identify the coverage of the corrosion, and very importantly, the deepest point of this corrosion. And just by one measurement, he's able to know if he will be able to remove these 271 micron to get rid of the corrosion, or if they will have to unfortunately scrap the part and replace it by a new one. So you see, just a scan, a few minutes of analysis, and you can take a decision, if you have to rework the part or if you need to replace it. And it has a tremendous value, in the domain of aircraft and aerospace maintenance in general.
Thanks, Thierry. So let's do another corrosion example that we have as well. So maybe there are going to be some scenarios where we want to measure corrosion in an area that's already that's a layer below what we're interested in. So if we measured the corrosion using the pit detection function here, which we'll go ahead and do, we'll see the depth measurement will be with respect to this area. But maybe we actually want the depth measurement with respect to this coated area where the coating has been removed. So we can use pit detection in conjunction with other functions to get the measurement result that we're looking for. So in this case, let's add our pit detection analysis here. We'll do something like this around this area, and we'll click Analyze. And we can see a bunch of pits in this area. We can sort the table based on depth and find the deepest point here, this blue dot. Now, the depth measurement that we're getting is about 64 micron, but that's going to be with respect to this area. But maybe I want to measure with respect to this surface here. So once I have this minimum point here, I could make a note of that. And maybe we want to actually measure something like that. So I drew this ruler tool just as a reference point. And now I'm going to add an offset function, which we went over in the last webinar as an example of something to use on edges. But here's another scenario that we can use when we're looking at essentially a step height. So I'm going to go ahead and draw a line through what I'm interested in measuring here. And I'm going to add my reference surface. We'll just add that on this side here. And we can see, let's take this. Maybe we want to measure the deepest point, or maybe we want the average, but I'll set it to minimum for now. And we can see the actual depth measurement is going to be about 177 micron when we're using the area up here as the reference surface rather than the area around the pit itself. So this is just kind of another example of how to use pit detection when you might want to use another tool with it as well. So another corrosion example that Thierry mentioned is in the introduction. was talking about buildup and that before pits are formed. So to do that, we're going to switch over and use our particle detection function. So pit detection will only detect negative features, but we also have corrosion examples where you're actually interested in the positive material buildup rather than just the pitting. So I'll open up this scan that we have here, and let's take a look at it in 3D so you can see that this is kind of positive material. I'm going to decrease the scaling a little bit, and you can see all of that buildup on this part. So for this, we'll jump back to analyze here. And I'm going to go ahead and add our particle detection function to look for positive features. And we're going to let's draw a shape, something like this. And we'll click Analyze here. So we can see that it's picking up all of these positive features in our field of view rather than negative ones. In this case, we might even want to turn on the ROI border particles as well to get those ones that are on the edges, but it'd be application dependent. But here we go, we just enabled that, and we can see it picking up these this other buildup around the edges of our region as well. So our particle detection function looks pretty similar to the pit detection function, but we do also have some other outputs that are available for this, and those are specific to cleanliness applications. So I'll actually go ahead and I'll take another scan, and let's talk about some of those other outputs that we can see in particle detection. So we'll jump back to capture here. And I'm just going to scan this flat target here. It's just a piece of glass on here. And I'm assuming we've picked up some dust. So we're going to go ahead and measure some dust and particles that are on the field of view here. So we'll take this scan. And we'll put that down. And let's open up our new scan. So we can see a couple particles in the field of view, and let's go ahead and add our particle detection algorithm here too. And I'll click Analyze. So now you can see it highlighting all of there's a little fiber and a couple of dust particles that have been collected on this target as it's been sitting here. And let's talk about some of these other outputs. So we can still see the number of particles. We can also see the number of particles scaled. And this is specific to the cleanliness standard CC1246E. So we have some of the outputs specific to that available here. So the number of particles scaled basically refers to the number of particles multiplied to account for the area that is covered in this reference standard. And we also have the analyzed area and the cleanliness score. And the cleanliness score is calculated based on binning of the particles that were found in the field of view. So you're allowed a certain number of particles of certain sizes, and based on that, we'll give you the cleanliness score. But one of, I think, the most interesting outputs of the particle detection function outside of cleanliness that is part of cleanliness as well is going to be the histogram. So I can see right now we've got you can see this tab here. It says CC1246E histogram. And this will actually give you the particle size distribution based on diameter of the particles in the field of view. And this is really interesting and relevant for a lot of other use cases and applications as well. A couple that we'll show you now. So I'll jump over to another scan that we took to kind of show a unique application with the GelSight system. We'll come to alphabetical. There we go. You can see this scan here that's labeled Crest Kids. And it's labeled Crest Kids because it's Crest Kids toothpaste. So this is an actual scan of toothpaste taken with our GelSight Max and a silicone gel. So we'll just define a region. Actually, we could just run this on the whole field of view. And I'll click Analyze here. And this one's a 16 megapixel image. It's a larger scan, so it takes a little longer to process. That's what we're seeing right now. And we can see it picking up all of these particles. And I know that we're actually looking for some smaller particles in this, so I'll actually go in and even change the default settings to find some smaller particles here. So in the personal care world, maybe you have some sort of exfoliating product, whether it's toothpaste or a cleanser, and you want to look at kind of the particle size distribution within that material. We can do that with GelSight too. So now you can see it picking up a bunch of these smaller particles here. And we can take a look at that histogram, which could be different across different types of products, right? And for the last example that I wanted to share, this one I think is a GelSight favorite internally, but I'll open up this scan here. And this one is a scan of snow. So since I'm based in New England and we had 5 inches of snow last week, I actually took this scan then. But this is a real application that we have with the Norwegian ski team. So maybe Thierry, while I do this, do you want to talk a little bit about that application?
Yeah, we started to work with the Norwegian Olympic ski team a few years ago, and we were surprised to learn that they were using our system, portable system, to measure, the roughness and also the structure of the compacted snow just before the competition. So basically, 4 in the morning, -20 C, they are on a track measuring, the roughness of the snow. Going back to the bungalow, preparing, the skis for the champion with the right wax. And so it's really impressive, the way they are really extracting all this information from our technology. And in terms of value, at the end of a race, maybe the difference is between, a silver medal and a gold medal. And for this champion, it's tremendous. We don't pretend that they win, the gold medal because of GelSight, but we are very, very proud to participate to this success.
Thanks, Thierry. And so maybe, Thierry, could you also talk a little bit about the value that GelSight brings for these types of applications?
Yeah. You were talking about cleanliness of components. You need to know, and I'm sure people know around the table, that in the space industry, cleaning a component is a very complex phenomena. You need to take the component, to bring it to a lab, to rinse it with the solvent or deionized water. Then the liquid, you pass the liquid through a membrane, and you take the membrane and you count it visually, with an operator or using a very costly microscope. And so it's a very long process, and it takes forever. And what we have seen with the use of our function is that just taking a scan locally directly on the part, and you have the answer. So once again, same thing, it brings a huge value to shorten, the long processes which occurs in the space industry.
Yeah, and I think, could you share a little bit more too about some of the challenges for other systems, maybe for corrosion or?
Yeah, for corrosion, it's extremely complex because today what people are using is just a depth gauge or optical micrometers, and you just do a measurement on a single pit. So you try to select the deepest one, but it's almost impossible to do. And most of the time, in the maintenance workshop, they just scrap the part and then don't take the risk to rework it. GelSight really brings a unique tool to take the decision: should I keep the part or not? And it's also a very good way to exchange with your customer, because sometimes the customer asks you the question, why did you replace this part? On which quantitative data? And with GelSight, you bring the proof that unfortunately I was obliged to replace the part and to replace it by a new one. So it's really the value is everywhere when you use, the GelSight tool in these industries.
Thank you, Thierry. So I think with that, we'll wrap up and answer any questions that have come in the Q&A. So feel free to ask some more questions now. And it looks like Frank has answered a couple in the Q&A, and maybe we'll cover those so that everyone can hear them as well. So we did have one question that was, what is the smallest pit that can be picked up? And I think Frank shared the minimum nominal feature size that we can enter in the software, but I thought it'd also be worth mentioning the accuracy specs in the Z direction for this. So with the system that I'm using today, the Series 2, the accuracy in the Z direction is going to be 1 micron plus 4% of the nominal depth. And we also have a Mac system where the accuracy in the Z direction is going to be 300 nanometer plus 4% of the nominal as well. And it looks like we've got another question here too that says was asking about output settings. So I know I've been speaking in metric and all of the demos in metric, but we can just quickly switch between measurement units with a radio button, and it'll automatically update to your whatever measurement system you select. So that is a quick setting. Maybe the next webinar we'll do in imperial units. We'll see.
I will suffer.
Yeah. All right.
Yeah, I think there is also a question about, doing this kind of measurement on curved surfaces, cylindrical surfaces, and yeah, definitely there is no limitation due to the complexity of the shape on which you want to do the measurement.
Right. Yeah. So when we talked about the Gaussian filter that's applied to remove the reference surface to highlight the pits, that's kind of factored in that area there. All right. And we have the next question here. It says, is the non-contact 3D surface analysis just made with the camera or also with laser technique? So the GelSight system is a contact-based system, but it is going to be non-destructive contact. We have a soft gel sensor. It's kind of like your fingertip. So we are taking images of the surface through the contact of the gel sensor. This gel is going to be what conforms to your surface. And we have another question here that says, could we have a copy of the recorded webinar? Yes, we'll be putting it on to YouTube from here. So once it's downloaded after this, we'll get it uploaded to YouTube. And I think we'll be sending an email out to everyone that joined and everyone that missed it, so that you can reference that. It was with respect to training inspectors at your facilities too. And so if you have any other questions, you're welcome to reach out to myself or Frank at support@gelsight.com, and we're happy to help you develop customized training for your inspections as well. We do have a question that says, is the accuracy of the pit depth limited by the pit width? 1-to-1 ratio is my understanding. Yeah, so that's a good point. The gel does need to make contact with your surface for you to measure it. So in the example of a pit that's very narrow, but very deep, we might not get to the bottom of it. So there is going to be some limitation of gel contact and then eventually illumination getting into very small but deep pits. Yeah. The good thing is you do get a visual indication of if you're seeing the bottom. You can always open that scan up and you'll see if you're making contact with it or not. Thierry, I don't know if you wanted to add anything to that. I know we have some people using the tool where we will still measure to what we can reach. So
yeah, you clearly answered to the question. We need to have contact between the gel and the surface to make an accurate measurement, and the aspect ratio needs to be greater than 1 when we consider the aspect ratio between the width and the depth of what you want to measure. It has to be greater than 1. Absolutely. Is the reason why during the introduction I really mentioned that we are not able to measure, of course, the corrosion which creates galleries under the surface. it's unfortunately these type of corrosion we cannot have access to, but there is no easy solution to have access to, for sure.
Thanks, Thierry. We have another question here. It says, with respect to the gel surface pad, can it be cleaned off easily? We use it on toothpaste. How do we clean it without damaging the tip? They'd use it maybe on fuel sealant potting material that's mostly cured, for example. So for this one, we do have a few different gel formulations. I mentioned the toothpaste one specifically, we used a silicone gel for. But application dependent, we can pick whatever gel makes the most sense for your application. The gel that I'm using today has a low friction coating on it, and we just clean it with a dry foam swab. This might not be the gel we'd recommend for that, but some of the other gels we just clean with blue painter's tape or even water. We've also done some studies on cleaning with germicidal bleach for biology related applications that need to really get rid of any sort of possibility of transfer of I guess materials for that. So we have some options. So we feel free to reach out, and we'll follow up with you as well about your use case, and we can see what makes sense for that.
Yeah, there is also a question about to just take a scan and have the result right away. So in the GelSight mobile software, you can automatically launch the function you want to use, and then you will have automatically, just after the scan and also the 3D reconstruction, the results of the analysis you want to make. This can be fully automated. And there was also another question regarding the integration of a GelSight probe at the end of a robotic arm or an arm. This is also something which is feasible. We have a version of the probe with mounting holes, and it's extremely straightforward to install the probe at the end of an arm, for example.
Thanks. I also see another question here that says, can this be streamlined for specific applications? For example, you have maybe a part number that has this one specific area and dimension and tolerances, and maybe another one that has another set. So similar to how Thierry mentioned, we can run these as a routine in an automated way. We can also clone all of these functions and have different inputs and tolerances for them as well. So we could have pit detection part A, pit detection part B, and they could have different input shapes and different parameters as well as tolerances for pass-fail criteria. We've got time for maybe one or two more questions. They keep flowing in, but we'll make sure we follow up after the fact with anyone that we don't get to. Do we offer on-site training or even on-site demos? Yes, we do. We're happy to do on-site training. We have on-site training, virtual training, and we have people located across the US. I'm in Massachusetts, and Frank, who's answering the Q&A in the chat, he's in the Bay Area. But yes, definitely have options for on-site training. And then, does the temperature affect the gel and measurements? So we talked about the snow application, but obviously we also have applications where it's going to be pretty warm. I know people are using our system outside to measure scratches on fuselage, so it's going to be kind of the opposite of snow, right? So the ambient temperature isn't going to have an effect on the measurements. In the case of the snow one, I think this is just interesting to add. If you just went and make contact with it directly, you will see the snow start to melt a little bit. So what they do in that application is they actually hold the probe on an area that they're not interested in measuring to cool the surface down. And then they go scan the area that they want to measure so that the snow isn't melting when they take the scan. All right. And I think that's probably all of the questions that we have time for today, but the Zoom will let us download all of them, and we'll make sure that we follow up directly to answer the rest of them. So thank you all for joining us today, and you'll get a notification when we get this downloaded and uploaded to YouTube as well. So thank you all.
Yeah, thank you very much, all of you. Thanks.